Okay, Lecture 25. I'd like to look at Servo Compensator design using LQG methods. Now, as a recap, what a Servo Compensator does is it lets you track a set point. If I want to track a constant set point, I'll add an integrator to integrate the difference between my output and my set point. What the Servo Compensator does is at steady state, by definition, x dot equals 0, or z dot equals 0, forcing y to equal r. The servo does is it finds out what constant do I need to bias the input to force y to track r. I can also design servo compensators to track sine waves by having poles, dynamics in the servo compensator. Right now we'll just look at the case where I want to track a constant set point, since that's most common. The closed loop dynamics of a plant plus a servo compensator as follows. The challenge I want to come up with, or the problem I want to solve, is how do you find kx and kz using LQR techniques. As an example, let's just look at a fourth order heat equation, basically a four-stage RC filter. So here you have your x dot equals ax, there's your A matrix, here's your B matrix. The output is the fourth state on the RC filter. And I have a servo compensator. I'm going to integrate the difference between the output, state 4, and the set point, r. Using LQR techniques, what I want to do is find my feedback gains, kx and kz, so that there's no error per step input, which is kind of granted given a servo compensator with an integrator. That's given. I want a 2% settling time of 4 seconds and less than 4% overshoot per step input. One approach. I've got a bunch of states. The state that I really care about is the fourth state. That's the output. So it would make sense that I want to weight the output, weight position x, or weight y. So Q will just be C transpose C, where C is the gain of the C matrix corresponding to y equals Cx. Problem with that. If I try using LQR techniques with a servo compensator and having Q just weighting the output y, I get an error. The error is trying to tell you something. The challenge is trying to figure out what the math is trying to tell you. One way to fix the error is if it doesn't like that Q matrix, let's just add a 10 to the minus 3 times the identity matrix. This is kind of a kludge, something small, so essentially what I'm doing is I'm weighting the output state, y, plus something so I don't get math errors. Second problem. If you do that, what I'll wind up with is my Q matrix is basically 0. That's your 0.01 on the diagonals. Here's what I care about. I want to force y to track the set point. If I do that, I'll have very small gains, and my pole is very, very slow. Again, that's not really a problem. If my system's too slow, crank up the gain, increase Q. However, third problem is if I do that, now crank up the gain on the state that I care about to 1,000, that just made things worse. I'm now really, really, really slow. So the idea of weighting the thing that you care about, ignoring the servo states, things I don't care about, doesn't work. The reason it doesn't work is the math is dumb. It sees this system. I've got an integrator. I've got a state y. It thinks this is the output. By weighting y, what I'm doing is I'm saying get to steady state really, really slowly. I'm weighting the derivative of the output. So likewise, when I increase the weighting on y, I just get slower and slower. Instead, what I should do is kind of counterintuitive. To make this system reach steady state quickly, I want to weight the state I don't care about, my dummy state z. Z looks like the output. Y looks like its derivative. So by increasing the weighting on z, I'm increasing the spring constant, essentially. By increasing the weighting on y, I'm increasing friction. And by iterating between the two, I can speed up the system and reduce the overshoot. So that's the second design approach. So I'd like to go through an example where I do that. I'm going to start iterating between increasing z till it's fast enough, then increase y to get rid of the overshoot. Going back to our requirements, what I want is the step response should look like the following. It should have a 4-second settling time, about no overshoot, and a DC gain of 1. So that's my desired step response. I'm going to sit there and vary Q and R until I get this response. Starting out, I've got my two outputs. This is state Z, is the fifth state. My input y is the fourth state, for the heat equation. And likewise, my Q matrix corresponding to Z, that'll be speed or spring. This is the output for position, looks like friction. Let's start with just weighting the servo state, the dummy state. Find the feedback gains, close the feedback loop, take the step response. The red line is what I want. The blue line is the actual step response. It's too slow. So what you do with LQR techniques when you're too slow is crank up Q. Iterating a couple times, keep on cranking up Q until you're fast enough. Eventually wind up with 10,000 for Q. That gives me the blue line. It's now plenty fast. I get this overshoot, however. To get rid of the overshoot, let's add friction. Friction comes in the weighting of the Y state. Again, doing a little bit of trial and error between increasing the spring, playing with the friction, spring, friction, going back and forth until the two look alike. Eventually wind up here. If I weight the servo state with 5,000, position Y with 10,000, I'll get this step response. That's almost what I want. That's kind of the design procedure with LQR techniques in a servo compensator. A little bit counterintuitive. If I weight the servo state, I'm speeding up the system. If I weight the output, I'm adding friction. That gets rid of the overshoot. By iterating between the two, I can get my desired response. That essentially is how you design servo compensators using LQR techniques.